Hello everyone. In the previous lecture, we have learned various processes, the work done by all of the processes and the total heat required or the exchange in these processes. We discussed namely the four processes: isothermal process, adiabatic process, isochoric process and isobaric process. Okay, and let's revise upon those formulas once and then we will do some questions based on them. Okay, so let's make out a table. Here is the process. Now we are dealing with the work done by the gas, denoted by W, and the heat exchange. Right? That is delta Q. Okay. So let's begin with the first process we learned. First process was isothermal process, and as we remember, delta U was 0 in it, right, as the temperature was not changing, and the work was given by 2.303 nRT log of V2 upon V1. And as the first law of thermodynamics equation says that delta Q is equal to delta U plus W, and delta U is equals to 0, so delta Q is also equal to 2.303 nRT log of V2 upon V1. Right. So the second process we learned was adiabatic process. In this we knew that the system is cut from the outside, so we know that delta Q is equals to 0 in it. Now we know that delta U and W are opposite of each other, right? And they have the same magnitude, and one is positive, one is negative. So we can say that work is nothing but negative of nR delta T upon gamma minus 1, or this could be written as P1 V1 minus P2 V2 upon gamma minus 1, right? The third process we did was isochoric process. In isochoric process, you know that the volume of the container remains constant, so the work is basically 0. As the volume changes, 0. Now we can say that delta Q is equal to delta U by the first law of thermodynamics. So we can say that delta Q is nothing but equal to delta U, which is nothing but nR delta T by gamma minus 1, right? And the last process we did was isobaric process. For isobaric process, the work done is nR delta T, right, or P into delta V, right? And delta Q is nothing but addition of delta U plus delta plus W, that is NCP delta T, right? This is basically the table for the various work done and heat exchange for all the processes. You must remember all the equations, like what are the constraints followed in each of the processes. Let's begin with the isochoric process. We have volume constant, so we have pressure proportional to temperature, that is to say P1 upon T1 is equal to P2 upon T2, right? The second type of process we did was isothermal process, in which temperature was constant, right? So if the temperature is constant, we know that PV is equal to constant. So we can say that P1 V1 is equals to P2 V2. Alright. The third process we did was isobaric, in which the pressure is constant, and we have volume is proportional to temperature. Therefore, V1 upon T1 is equals to V2 upon T2. And the last process we did was adiabatic process, which has the property that PV raised to power gamma is equals to constant, which we can say that P1 V1 raised to power gamma equals P2 V2 raised to power gamma. Right. It could be written in other forms as well, like it is written in the form of PV. We can write it in form of V and T as well. So we get is T1 V1 raised to power gamma minus 1 equals T2 V2 raised to power gamma minus 1. And if we want to write in the terms of V and P or T and P, we can write it as T1 raised to power gamma P1 raised to power 1 minus gamma is equals to T2 raised to power gamma P2 raised to power 1 minus gamma. One equation is more than sufficient. You can derive the other two equations by just implanting the equation in the ideal gas equation, which is PV is equal to nRT. Like I will try and explain you one part. We are saying that P1 V1 raised to power gamma, let's suppose we had this equation, is equal to P2 V2 raised to power gamma. Using this, we did was P1 V1 into V raised to power gamma minus 1 is equals to P2 V2 into V raised to power gamma minus 1. Right. So P1 V1 could be replaced by nR T1 into V1 raised to power gamma minus 1. Similarly, here also nR T2 into V2 raised to power gamma minus 1. nR gets cancelled out. We get T1 V1 raised to power gamma minus 1 equals T2 V2 raised to power gamma minus 1. So this helps us derive the second equation. Similarly, you can derive the third equation. So till now we have discussed, we have just revised what we have learned in the previous lectures. Basically, the work and the heat exchange of each and every process, and what are the equations or constraints governing these equations. So let's try and do some questions based on the learning we had done so far. Okay, so let's begin with the question. The question says that an ideal gas undergoes an isothermal process of expansion at 0 degree Celsius from 0.010 meter cube to 0.200 meter cube. For 5 moles of the gas, what is the work done, the heat absorbed, and delta U? Right? You have to find all these. First of all, you have to know the signs of the values. Just by looking at the question, you can know what values would be positive, what values would be negative. So first of all, it is given that the process is of expansion. As the volume is expanding, we know that W would be positive, right? In isothermal process, we know that delta U is always equals to 0, and delta Q therefore is equals to delta U plus W, which is nothing but delta Q is equals to W, right? So the basic thing we have to do is find the work done by the gas. So work done, as we know, is nothing but 2.303 nRT into log of V2 upon V1. Alright. So 2.303 into 5 moles of the gas into SI unit of R, that is 8.3, into temperature, which is 0 degree Celsius, which is 273 Kelvin, into log of 0.200 upon 0.010, which is nothing but point cancel out, 20, log of 20, right? If you compute this value, the work comes out to be 33.946 kilojoules. Okay, and as we know that the work and the kilojoules, and delta Q is obviously equal to W, which is nothing but 33.946 kilojoules only, right? So this was a straightforward question based on the concept of finding the work done of an isothermal expansion process, right? So let's try and do a bit different question. It says that a gasoline engine takes 5 moles of a gas of air at 20 degrees Celsius and 1 atm and compresses it adiabatically to 1/10 of the volume, right? You have to find the T final and P final, assuming air to be diatomic, which is a very sound assumption because air is nothing but majorly N2 and O2, which are diatomic molecules, right? And you have to find the work done as well and delta U, right? So these all things you have to find out. So first of all, let's realize what we are doing. So first of all, it is an adiabatic expansion process, right? As the expansion is taking place, you are very much sure that delta U would be negative and work would be positive, right, as it is expanding. And we know that delta Q is 0 in this case, which is equal to delta U plus W, and if work is positive, delta U would be negative because the gas is expanding on the expense of its own internal energy, right? So now you have to find the final temperature and volume, okay, final temperature and pressure. So we'll use the constraint equations of adiabatic process because they relate temperature and volume as well as pressure and volume of the initial condition to the final condition. So if we take T1 V1 raised to power gamma minus 1 equals to T2 V2 raised to power gamma minus 1. As it is diatomic, gamma is equal to 7/5, right? Initial temperature is 293 Kelvin. Volume was say B1 raised to power 2/5 equals to T2 we have to find out, and the volume is reduced to 1/10 of its volume. So it is V1 upon 10, 2/5. So let's take this term on that side. You get 293 into V1 upon B1 into 10 raised to power 2/5. Okay, so we get 293 into 10 raised to power 2/5, which is a value equivalent to 25,736 Kelvin, right? You can use a calculator in order to calculate the exact value. Now let's try to find the final pressure. The final pressure could be given by P1 V1 raised to power gamma equals to P2 V2 raised to power gamma, right? The initial temperature was given to be 1 atm, volume V1 raised to power 7/5 equals to P2 we have to find out V1 upon 10 raised to power 7/5. So this can help us to find P2, which is 1 atm into V1 upon V1 into 10 raised to power 7/5, which is nothing but 1 into 10 raised to power 7/5 atm, which instead gives us 25.12 atm. So this is the final pressure. Okay, now you have to find the delta U and work. Work, as you can see, delta U is equals to minus work in this condition. You know that delta V is nothing but NCV delta T. So we can find it for 5 moles. We are dealing with 5, or we can say it NR delta T upon gamma minus 1. So we can calculate for 5 moles into 8.3. Delta T is what? We have found the final temperature at 736 Kelvin and the initial temperature at 273 Kelvin. So if we subtract, it gives us 463 kelvins, the change in temperature. So we multiply it by 463 upon gamma minus 1, that is 2 into 5, which gives us the value -46 kilojoules. So work is just negative of delta U, which is -46 kilojoules. So the first question which we did was directly based on the formula of work done and realizing that delta Q was equals to work. But in the second case, we had to use the second question. We had to also use the constraint equation, which implies that the process is a adiabatic process. Using that, we found the final temperature and pressure, which helped us to calculate it. Okay. Now let's do another question, which says that how much work is done by an ideal gas on expanding isothermally from an initial temperature, from an initial volume of 3 liters at a pressure of 20 atm to final volume of 24 liters, right? So first of all, it is given that the process is isothermal expansion. So the volume is changing and the temperature remains same. And you have to see that why is it happening, right? So what is happening in the process? So work is nothing but 2.303 nRT into log of V2 upon V1, right? So this is the work done. Now you can say that here neither we have the moles of the gas, neither we have the pressure, neither we have the temperature of the gas. But we should understand that this is an ideal gas. So it is governed by the ideal gas equation, PV is equal to nRT. So if we are given pressure and volume, which means we are given with the T as well as the moles of the gas. Okay, so nRT can be calculated by multiplying pressure into volume. But we have to do it in the SI units, right? So we have to convert the left hand side into 20 into 1 atm, that is 1.013 into 10 raised to power 5 Newton per meter square into volume in meter cube, which is 24 into 10 raised to power minus 3 meter cube. So if you multiply this, we get 10 square over here. So this gives us 2000 into 24 into 1.013, right? So now if you try to calculate the work, which would come out to be 2.303 into the value of this, which is 2000 into 24 into 1.013 into log of 24 upon 3, which is 8, right? So which would come out to be nothing but 1.26 into 10 raised to power 4 joules. So the important thing in this question was to realize that we don't have to just put in or plug in the values in the formulas. We have to just manipulate the things we require from the things given, right? So if we are giving pressure and volume, we can calculate the value of nRT by using the ideal gas equation, right? Let's try and do one good question based on the PV curve we have learned. Okay. So the question says that the PV curve for an ideal gas for a process is given like this. This point is C, this point is A, this point is B, right? The volume is plotted over here as 8.2 liters. This is volume in liters and this is pressure in atm, right? At C the pressure is given to be 8, at A the pressure is 4, and here the volume is 16.4, right? So this is the PV graph and there is the process where this comes from C to A to B, and then goes back to B to C, right? So it is a cyclic process consisting of 3 steps from A to B, B to C, and C to A, right? So the question says that 2 moles of ideal gas are carried around a cycle like this, as shown in the figure, if process B to C, right, this one, the curved one, is isothermal. Okay, you have known that it is isothermal process, and CV of the gas is 3 calories per mole per Kelvin, right? You have to determine the work done. Second thing you have to do is change in the internal energy. C is heat exchange or heat supplied to the system. Okay, for all the 3 processes, that is from A to B, B to C, C to A. So it is the complete diagnosis of this structure. You have to find each and everything of this complete cyclic round, right? So let's begin with the first objectives. So the first objectives are the work done. So we are doing the work done for A to B, right? The first thing you must identify which all types of processes it is. As the pressure is seeming to be constant over there, this is isobaric process, right? Isobaric expansion. You are given that this curved path is isothermal process in the question itself, right? And the volume is decreasing, so it is nothing but isothermal compression. Okay, now the third process, in this the volume remains constant, so it is nothing but isochoric, and as the pressure is falling, so temperature would be also falling, so it is isochoric cooling, right? So we have first of all identified all the 3 processes, what is happening, and now we can find the work done for each and every process. Work done AB is the work done for a isobaric process, which is nothing but P delta V. So this could be calculated very easily. This is 4 atm and a change in volume, which is 8.2 liters. So this gives us 0.8 into 32, right, liter atm. Now we can use the conversion from 1 liter atm to joules, which is nothing but 101 joules, right? So using this conversion, we can directly get the answer for work done A to B is equal to 3313 joules. Okay, now let's try to find out the work for the other process, which is work of B to C, right? BC is a isothermal compression process, right? So isothermal compression process, so the work done would be 2.303 nRT log of Vc, because it is final situation is C and the initial state was B, right? So 2.303, this could be replaced by PV because we don't have the value for temperature, etc. The values PV into log of Vc upon Vb, which is nothing but 2.303 into pressure and volume at that position, 4 into 16.4 log of 8.2 upon 16.4, so log of half basically, right? So it would give us minus of 2.303 into 4 into 16.4 into log of 2, minus we have taken out for 1 upon 2 and converted it to log 2. This is also the work as minus 459.2.5 joules. I have converted the value to joules as well. So we can directly multiply it by 101 to get the answer in joules. So this is the work done from B to C. Now let's try to find the work done for C to A, which is the isochoric process. So the volume is not changing, so the work is directly equal to 0. Right. So the first part we have done for each and every process. Now let's try to find out the second part, which is nothing but the change in internal energy. Right. Change in the internal energy for, that is delta U for process A to B, which is given by NCV delta T upon, which could be written as NR delta T upon gamma minus 1. Okay. Or we can write at this as P1 V1 or PA VA minus PV VB upon gamma minus 1. Right. Okay. So we can do it in this way. So first of all, there is one difficulty in this process is we don't know which type of gas it is. Right. So we don't have the value for gamma minus 1. This is a special type of problem that you might face at some of the times. You don't know which type of the gas it is. So there is an escape for this. That's why it is given. Right. Because you are not having the value for gamma over here, but you have the value for CV given to you already. Right. Try and look in the question. It was given that CV is nothing but 3 calories per mole per kg. So you can use that over here. So N into N was 2 moles, right? 2 moles into the value of CV, which is nothing but 3 calories. Calories you have to convert it to joules by multiplying it 4.186, right? This gives us the value in moles joules, right? So then we have to find the delta T. Delta T means you have to find the temperature at both the positions. So it would be nothing but PB VB upon NR by the ideal gas equation gives us T2 minus PA VA upon NR. This gives us the temperature at point A, temperature at point B. So using this, substituting the values over here for pressure B as 4, volume being 16.4, PA being 4, PA being 8.2, moles being 2, and R being 0.0821 because we are dealing with ATMs and liters. Okay, so we can find the temperature A and temperature B, which gives us delta U for A to B as 1200 calories. Okay, or if you multiply it by 4.186, we get in joules, right? So let's try to find out the other processes work done. Change in internal energy. So delta U for B to C, as it is isothermal process, it would be obviously equal to 0, right? Then we are doing for C to A. Now the very important thing over here is, you can say that you started from A, you went to B, then you went from B to C. That is, first you started from here, you went like this, then you went from B to C, then you are coming back to C from C to A. That means in the end you reach the same position as a starting. And as you know, delta is a state function. It depends only on the states, which is to say that if you completed a round, your delta U would be 0 because you have reached the same position. So we can say that delta U C to A, delta U B to C plus delta U A to B would be nothing but 0. So which gives us delta U C to A as minus 1200 calories, right? Now I'm not calculating basically the value for heat. We can do it directly because for each process you have delta U and each process you have W. So you have to just add them to get the total internal energy. Total heat supplied. So in this lecture we did various questions based on the concept we have learned till now. We formalized the various formulas we require and the constraints. So the important thing in was problem solving is you have to first of all identify which all processes are taking in the process. Just look at the information given in the question. Like in this graph question, you had just to figure out which type of processes are taking place, and then you can identify whether it is expansion or compression and use the required formulas to find the answers. Thank you. In the next lecture, we'll do some more questions. Okay.